Now we're going to move to the second model of a simple harmonic oscillator, which is pendulum. Right, what is pendulum? When you have a bob, okay, a bob attached to a string. This string must be massless and unstretchable. Then the whole bulk of the calculation or derivation after this are valid. Right, so at this instant, okay, we displace the bob from here, the equilibrium position, to maximum angle of theta, to this position. At this instant, okay, at the moment we are going to release the bob, okay, at this instant the bob is experiencing tension due to the string, okay, away from it into this direction, and it's also experience weight, okay, attractional force to the center of the gravity. By mathematics, we can prove that this angle and this angle is the same. Alright, and then assuming that there is no air drag and internal friction at all, okay, then okay, we're going to have, okay, the component of the mg. Here is mg cos theta, and here is mg sin theta. Okay, and then not to forget that our initial displacement just now is the s is to the right, while the motion is to the left. Okay, so mg cos theta going to be balanced or cancel out with the t. The only one that unbalanced force is this one, the mg sin theta. Okay, if it is unbalanced, it means that this is the net force. Okay, this is the net force that going to cause the block going to move. Okay, so since the force here is tangent to the position of the block, okay, we may put a symbol of Ft to this force. Okay, then Ft is equivalent to MAT. Alright, T stand for tangential. Okay, why is it the AT? Because the motion is tangent to the point. So that is why we have Ft and AT here. What is our Ft? It's negative mg sin theta. Okay, why is it negative? Because it is to the left. And not to forget, this is equivalent to MAT. This is the whole part here is 80. Right, so here is your Ft. Right, and we do know that, okay, the length of the pendulum here is also the radius of a bigger picture, or the radius of the circle. Right, linear displacement, the S, okay, is equivalent to r theta, isn't it? If you still remember, S equivalent to r theta. So our r right now is the L. Okay, so that is why is equivalent to L theta, which is, okay, this is your S or linear displacement, equivalent to, which bring us to d square S over dt square, which is the AT just now, must equivalent to L d square theta over dt square. Okay, so this one is similar to this. Right, so one is d squared theta over dt squared, rearrange, this one going to be moved to this side. Then we also know that this one equivalent to this, and this one also equivalent to this. Okay, so if we see here, d squared S over dt squared is equivalent to g sine theta. So then we're going to put it here, negative g sine theta. Right, so That is why you may rearrange, okay, the d squared theta over dt squared, this one, d squared theta over dt squared is equivalent to negative g over L sin theta. Right. And bear in mind, for simple harmonic motion, you have to obey, you have to always remember, okay, our reference here is d squared x over dt squared is equivalent to negative k over m times x. The pattern here is almost the same to this pattern, right? So we may say that the simple pendulum, okay, also a kind of simple harmonic motion, with regards that the theta is small where it less than 10 degree, right? Now, if the theta is very small, sin theta, okay, for this reference, sin theta more or less to theta only. Alright, then you are going to simplify the equation into this. Instead of having sin theta here, we are going to have theta only. And for simple pendulum, the position of theta at any instant in terms of sinusoidal wave function going to be theta max cos omega t plus phi. This is actually in comparison to x equivalent to a cos omega t plus phi. Right. And from here, we know for this case, okay, omega equivalent to square root k over m, and for this case, okay, it's omega equivalent to square root g over L, right? And from here we know that t is equivalent to 2 pi over omega. So what is our omega? Is square root g over L. That is how this equation become like this. Alright. So a proof of for a small value of theta, okay, sin theta more or less to theta here, my dear, is 0 degree, 1 degree, more or less, right? 0.0 is almost 0. Okay, 0. Angle in radian, sine. So almost the same. This is the angle in radian, this is the sin of it. Almost the same. So we take it as up to 10 degree. Okay. Example 15.5, a connection between length and time. Okay, we have Christian Huygens, okay, the greatest clockmaker in history, suggested that an international unit of length should be defined as the length of simple pendulum having a period of exactly 1 second. Okay, how much shorter would our length unit be if his suggestion had been followed? So based on the formula of a period is equivalent to 2 pi square root L over G. Now our interest, we want to know our length, the L. Okay, rearrange the equation, substitute the T needed is 1 second, and the G, take it as the well-known G, which is 9.8. Then you will have this length, 0.248 meter, to produce 1 second. Okay. Okay, what if Huygens had been born on another planet? Means that the G going to be varied. What would the value for G have to be on that planet such that the meter based on Huygens pendulum will have the same value as our meter? From here, if we still want to have 1 second, the same reading to previous example just now, the previous part just now. So we are going to figure out the G. If you see here, 39.5 meter per second squared, which is not logic. Okay, this is not logic. I don't think we do have this amount of gravitational acceleration within any planet within our universe. Physical pendulum is a pendulum where we are going to use an object, undefined shape object, okay, we choose one point to be a pivot, okay, and we're going to oscillate this object. Okay, if the hanging object here, okay, oscillate about a fixed point which is chosen at this point, okay, that does not pass through its center of the mass. So this pivot is not passing through the center of the mass. Okay, how we know the center of mass here? Actually, you have to perform some calculation, okay, because this is undefined shape, so you need to figure out the moment of inertia and whatnot, and then you are going to know where is the cm, center of mass of the object. In this case, it is already given that this is a point for center of mass for this object. So the pivot, okay, or fixed axis here, okay, does not pass through the center of mass, and the object cannot be approximated as a point mass. This is big, cannot be replaced with a simple or point mass. Okay, so okay, we cannot treat the system here as a simple pendulum. So we cannot treat this one as a simple pendulum. For physical pendulum, okay, if you see here, okay, it's not passing through the center of mass of the object, and it cannot be replaced as a point mass, okay, in comparison to the bulb. Okay, just a point. Alright, in comparison to this, you cannot put it in terms of point. It's very big, massive. What is the one that causing the object to rotate, to oscillate? Okay, is actually the unbalanced force, which is the mg. Mg1 is not simply mg. The rotational or the oscillation is actually a kind of torque. Okay, so the torque is actually mg d sin theta. Okay, so mg is the force, d sin theta is the lever arm. Right, so sum of external torque external, okay, within the system must be equivalent to moment inertia of the system times with the alpha. So what is the torque external that exists here? Again, negative mg d sin theta. Why is it negative? Because the rotation going to be clockwise direction. Okay, what is alpha? Alpha is d squared theta over dt squared. Hopefully you still recall this one. And rearrange, if the theta is small, then sin theta going to be theta only. Right, so here you have it here. Alright, d squared theta over dt squared is equivalent to negative mgd over I times with the theta. And bear in mind, still, okay, the mathematical expression of theta, okay, as a function of time is according to the disk, which is in comparison similar to x equivalent to a cos omega t plus phi. And from here, okay, we may do some rearrangement and show that omega is equivalent to square root of mgt over I. If you have the omega like this, now you may substitute the information of t equivalent to 2 pi over omega, then you're going to have the t formula for physical pendulum. Right. Okay, example 15.6, a swing rod. Okay, a uniform rod of mass m and l is pivoted about one end and oscillates in a vertical plane. Okay, so this is a pivot. Okay, find the period of oscillation if the amplitude of the motion is small. Why is it there is a statement of this? When the amplitude of the motion is small, so the theta is small. So means that we can have approximation of this is a kind of physical pendulum. Right? then we may use this kind of formula, right? And T equivalent to 2 pi square root moment of inertia over mgd. And for this uniform rod pivoted at one end, okay, so its moment of inertia is 1 over 3 ml squared. How to know this? You have to refer back to the table when we talk about moment of inertia from physics 1. Okay, and then the m can be cancelled out, so you are left with this. This is the general equation for this situation, right? B. Suppose the pivot is moved to a small hole drilled in the rod at a distance of L over 4 from the upper end. What is the period of oscillation of the rod when it is hung from this pivot point and swing through small oscillation again? So, my dear, for this case, it means that you are going to have another calculation of I. Okay, but then this one, just leave it, because this is not part of your syllabus. Alright, just I'm showing you, okay, how to do it. However, don't worry, this is out of your syllabus for physics 1, if you still remember. Okay, and next one is torsional pendulum. Now we're going to move to torsional pendulum. In this figure, okay, show a rigid object such as this suspended by a wire attached at the top to a fixed support, which is our roof, let's say here. Okay, when the object is twisted through some angle theta, right, the twisted wire exerts on the object a restoring force, torque. Okay, it's not only restoring force, it's restoring torque. Okay, that is proportional to the angular position. That is why, right, torque is equivalent to negative kappa times with the theta. So, why is it negative? Kappa is, firstly, kappa is Greek letter. It's called as torsion constant, okay, of the support wire, and is a rotational analog to the force, okay, which is K for a spring. So this is in comparison to F equivalent to negative Kx. Okay, and then the value of kappa can be obtained by applying a known torque twist to twist the wire through a measurable angle. Applying Newton's second law for rotational motion, you can find that sum of the torque, okay, is equivalent to I alpha. Okay, this is the Newton's second law of rotational motion. So your torque is now negative kappa times theta, and I times with the alpha is d squared theta over dt squared. Okay, so from here you may rearrange d squared theta over dt squared, the alpha just now, is equivalent to negative kappa over I times theta. From here, in comparison to the d square x over dt square equivalent to negative omega x, right? So here we can have our omega equivalent to this omega squared. Forgot, right? Then t is equivalent to 2 pi square root I over k. Okay, next one will be damp oscillation. Damp oscillation, whereby the previous that we've learned, all of it, all the system, whether torsional, whether physical, whether simple pendulum, where the mass spring system, all of it are ideal case. We consider there is no friction at all, any kind of friction or friction or any kind of resistance or drag, okay, that going to cause the oscillation going to slow down and eventually stop. But in real life, okay, in real life that is not the case. As we know, when you swing a pendulum, okay, that pendulum eventually going to stop, isn't it? Therefore, what happened actually, there is a case of damping process, or we call it that kind of oscillation is damp oscillation. For example, a mass spring system here is placed within a very viscous liquid. Okay, once you vibrate the system going to slow down and finally stop. Right, same goes to the disc bridge. Okay, it use spring attached to this bottom. So whenever the bridge is going to swing, okay, the vibration going to be absorbed by the mass spring system here, that going to slow down and stop the oscillation. Right, goes the same where we can apply the same thing in the car absorber or any other system that going to slow down and finally stop. Okay, for this case, we are not going for damp oscillation. We are not going to do the details of the equation, because in your learning outcome, you must be able to know to differentiate and to sketch the types of the damping process and differentiate them. Okay, so about the equation or formula, you may discard the damp oscillation. This is the general graph of it. Okay, means that the amplitude, how we know that one kind of oscillation is having damping process, whenever the amplitude of the oscillation decreases. Okay, how it decrease by this factor, which is one we're not going to discuss in detail, right, with the time. And then we have three types of oscillation. Okay, this is actually figure 15.22, page 405. Blue curve is under damp. This one is under damp. Okay, so this is similar to this figure just now, right? Okay, almost. And then the red color one is critically damp. The black color one is over damp. Okay, how to differentiate in terms of time? This one we can, if to make it simple, let's imagine you are within a cheapest car in Malaysia, let's say Kancil, right? Okay, so if you're facing a hole, okay, passing through a hole, then you're going to have an experience of this under damp. Okay, it's vibrating. Okay, you as the passenger going to feel the vibration within the car. All right, and then if let's say this is a better one, medium price Persona, or you can also have a Mazda, let's say Vios. Okay, then you're going to experience slightly a vibration, but then is going to be absorbed within a very short time. Is going to be no more oscillation. You're not going to experience any oscillation. How about this one? This is even the premium class. Okay, let's say you are Peugeot, Continental, Merc, okay, BMW, Audi. Okay, so you don't even realize that you're having oscillation. You are having your oscillation. This is what we call it over damp. My dear, make sure you know to differentiate this and also to sketch this graph. Okay, you must be able to differentiate and to sketch the graph here, right? and force oscillation. So whenever you have a damping, you have resistance that going to slow down the motion, and somehow you need or you want to make it oscillate according to whatever you want. For example, you play with your system, swing. Okay, so once you set the swing, okay, and you do not push anymore, the swing going to be eventually going to slow down, isn't it? And your sister keep on arguing you to push back, okay, more and more and more. So to make sure the swing going to smoothly swing according to the needs of your sister here, okay, you are going to push. Okay, after few swing, then you're going to support the system with another push. Okay, the push that you are giving to the sister just now is actually a force. Okay, so force oscillation means that we supply something to the oscillation, the system, so that the system remain, remain within the condition that we need or we want. Alright, so as we know, the F that we're going to apply, okay, as a function of time is equivalent to F naught sine omega t, okay, and then Fx equivalent to Max, okay, and then you may substitute everything here. So since we are not considering this equation in previous part, for this one also we are not going to be in detail about the equation. Just that force oscillation means that you are going to supply some additional force, okay, to the system, so that the system going to keep its swing or oscillation according to what we want, right? So the force oscillation, okay, going to give us some reading, okay, or the force oscillation just now, the force that we apply just now having some frequency, right? Okay, that force we known as driving force. If let's say the driving force that's applied to the system, okay, is equivalent to the natural frequency of the system, the oscillator, resonance going to occurs. This is a condition to have resonance, where, okay, the omega that you supply must be equivalent to, at least equivalent to, natural frequency of the system. Then consequent of it, resonance going to happen. Okay, what is resonance? Resonance where you have maximum output of your system. What is the output of our system? Is the amplitude, because amplitude is the displacement from the equilibrium position. So when it reach natural frequency, you're going to have maximum output like this, a graph like this. Okay, so this is what is resonance. Resonance sometimes not so good for us, sometimes it's good. Okay, this is for example where long time ago there is a bridge built up without considering the wind, okay, that exists within this area. So if you see here, firstly it's kind of swing, and eventually the natural frequency is reached by the force coming from the wind, and consequent of it, the bridge collapse, maximum amplitude, the bridge vibrate and reach its maximum amplitude, that causing a part of it going to be break. That is all for the resonance and also for this topic.